In this video, we're looking at the normal distribution. So we've got our bell-shaped curve over here, and we're looking at determining what percentages of our data will fit between certain values. So on our formula sheet, we have the normal distribution, the bell curve, and we've got those percentages, 68% between that -1 and 1 Z scores. So that means if we're 1 standard deviation from the mean, 68% of that data will fit between there. And then those other 95% values at 99.7%. Here's our first example. The masses of adult female koalas in a colony are normally distributed with a mean of 9.5 and a standard deviation of 0.8 kilograms. What percentage of these females would you expect to have masses between 7.9 and 10.3? I'm just going to underline percentage as well, because that's what we're trying to find out. Now, as soon as we see this normally distributed, that term there, we're going to be looking at drawing ourselves a nice little diagram. So we've got our bell curve, doesn't have to be beautiful, and we're going to pop our mean, which was 9.5, in the middle of that bell curve. Now, using our standard deviation of 0.8, we're going to go to the right and to the left a couple of steps. So adding 0.8 to our 9.5 gives us 10.3. And subtracting to the right gives us 8.7. So 10.3 here is already our value, our upper limit that we're trying to find, but we need to go to the left one more to find that 7.9, which if I subtract my standard deviation one more time is what I will end up with. And I'll just go one more step to the right so we can keep that symmetry. So adding to the right will give me 11.1. Just changing colors here so we can see those steps out to the left and right. So what we're essentially trying to find is we're trying to go from this 7.9 value here up to our 10.3 value over here. So if we look at that middle section, just going out by that first standard deviation, in that middle section in here, that's going to be 68%. We already know that. If we go out one step further, I'll just do that in green for the moment, all the way up to here, and it include that middle part, that's going to be 95%. So if I include all of this, that's going to be 95%. We know that as well. What I need though, is I need to get from our 7.9 up to our 10.3. So essentially what I need is I need that 95%, but I need to subtract the orange part over here. So the way I'm going to do that is I'm going to start with my 95%. I'm going to subtract that 68%. That's going to leave me with those two outer parts, and I'm going to divide it by 2. I can do that because of the symmetry of the normal curve. And what that's going to give me is 13.5%. So that 13.5% is this orange section on the right that we can see over here. So in order to find the area that we actually need, I'm going to keep my 95%. That's that whole section between 7.9 and 11.1, and I'm going to subtract that extra part that I don't need, that 13.5. So that gives me a total of 81.5%. So that's going to be this whole section from 7.9, including this middle part over here, up to 10.3. So we've completed that example now. So here's our second example. We've got a scientist measures the mass of a hive of bees, finds that they are normally distributed with a mean of 0.12 grams. A bee is considered underweight if its mass is less than 0.096 grams. And he finds that 0.15% of the bees are underweight. We want to know what the standard deviation is. So we've already been told that it is normally distributed. So we're going to start with our bell curve. And we're going to pop our mean 0.12 in the center. Now, looking at our bell curve, I'm just going to pop our 3 standard deviations in both directions out here. And I'm looking at this 0.15%. So 0.15% are underweight. So they're going to be less than one of our values on here. We know that 99.7% sit in that middle section, 3 standard deviations out from the mean. Now, if 0.15% are underweight, we're going to be looking at this section over here because 0.3%, I should say, are going to sit in both of those 2 sections. That's just our 100, take away our 99.7. So the section on the left, the less than side of that, which I'll just make red, is going to be half of that. So we know we're referring to this left-hand side section over here. We also know from the question that if it's less than 0.096, then it's considered underweight. So we can say that that section over there, less than that 0.096 is going to go there. So what we need to do is we need to figure out our standard deviation. If we are 3 standard deviations from the mean, then that tells me that 3 standard deviations, or 3 sigma, is equal to the difference between the mean and that value there. So 0.012 minus 0.096, we're 0.024. Just forgot that 0 in there. So 3 standard deviations is equal to 0.024. So then dividing by 3 will give us 1 standard deviation. So that's going to be 0.008. Now, this question here was actually a multiple choice question. It's come from a past trial paper. So this would be a 1-mark question, and this value here was one of our 4 options. Okay, so for our final example, we're actually going to look at the Z-score, or what we could call the standardized score. On our formula sheet, we do have this formula here for calculating the Z-score. So the Z-score is equal to whatever score you are looking at in your data set minus the mean itself divided by the standard deviation. So we can use that formula to calculate the Z-score if we know the mean and the standard deviation and we're looking at a particular score in our data set. Or we can figure out the mean or the standard deviation by forming an equation if the Z-score is known. So we'll look at this example here. The weights of boxes of Breckie are normally distributed. The mean is 754 grams and the standard deviation is 2 grams. Oops. So there's our mean and there's our standard deviation. We want to know what the Z-score is. So here's our formula up here, Z equals X minus mu over sigma. For a box of Breckie with a weight of 754 grams. Now, we could go ahead and substitute our values into our formula. So we could do 754, which is our score, minus our mean, 754, over 2, which is our standard deviation. Or if we just think about this for a moment, if our mean and our score are exactly the same, then that means on our bell curve, a z-score of 0 sits right in the middle, which is where our mean sits. So our z-score in this case is just going to be 0. So that tells us that our score is exactly the same as our mean. So no work required there. What is the weight of a box that has a z-score of -1? So in this case, I'm going to use my formula. So my z-score is -1. It's going to go as the subject on the left-hand side. Then on my right-hand side, I've got the fraction. We want to know the weight of the box. So we want to know what is the score, what is x. We know what our mean is, and we know what our standard deviation is. Then we're just going to solve this equation. So multiplying by 2. And then solving, I'm just going to move x to the left-hand side, and adding my 754 will give me 752 grams. So that's question 2 complete. And if we just look at part 3, we want to know Brockie Bix boxes are labelled as having a weight of 750 grams. We want to know what percentage of boxes will have a weight less than this. So we'll just draw ourselves a slightly bigger version of that bell curve with our 754 in the middle. And let's go to the left because we're looking at the less than. We're going out 2 grams at a time. There's our 750. It's 2 standard deviations to the left. Now, if I go 2 to the right as well, just to keep that balance, we know that as we go out 2 standard deviations, we have our 95%. So if we're looking at the less than part over here, using our symmetry, we'll have 100, take away 95 to give us our 2 sides of that, dividing it by 2 just to give us the left. So that's going to leave us with 2.5%. Will be less than that 750 grams.